found this problem or stumbled upon it, problem that was posted a couple years ago that was never answered, and thought I'd give it a shot. So we're supposed to use mathematical induction to show that the definite integral from 0 to infinity of x to the nth, where n is a constant, times e to the minus x is equal to n factorial for all n greater than or equal to 1. So first of all, the pictures on this page help to convince us that this indeed is true. So here's the original function where letting x be 1,000 is like letting have the upper limit be infinity. So when n is 1, the f of 1,000 is 1, and n factorial is 1. And if you look at the rest of these pictures, if we increase n to 2, and infinity, f is 2, and n factorial is 2, and so on. You can and look at this one. When n is 12, f at infinity is 479 million, and so is n factorial. Okay, so how do you do this with math induction? So there's two parts to proving something by math induction. First, you have to prove when n equals 1 that this is true. So we want to show that when n is 1, the result of this thing is n factorial, or 1 factorial. So we should get an answer of 1. And since this upper limit is infinity, we'll take the limit as a approaches infinity of the definite integral from 0 to a of this integrand. And we do that by parts. So we'll let u equals x, dv equals the antiderivative of everything, du and v. So the antiderivative is found by u times v. That's minus x e to the minus x minus the antiderivative of v du. So that's minus some e to the minus x dx. And we can move this minus sign out front, and the antiderivative e to the minus x, there's your antiderivative. Of course, you could say plus c, but we're going to use this part to replace this, because the antiderivative of x e to the minus x is this thing right here. So if I rewrite that with the e to the minus x in the denominator, evaluating from 0 to a, put a in for x. This is what you get. Take the limit as a approaches infinity. This term right here, you have to apply L'Hopital's rule because it's infinity over infinity. You get 1 over e to the infinity, which is 0. And there it is, 1 factorial, or 1. Okay. Now the second part, we have to suppose that the formula is true for n equals k and show that it follows that it's true for n equals k plus 1. So in effect, we're given this is true. From 0 to infinity, x to the k e to the minus x dx equals k factorial. And if that's true, we're supposed to be able to prove this. So this is what we want to evaluate and show that it equals k plus 1 factorial. So that will be the limit as a approaches infinity from 0 to a of this thing. Well, we better find an antiderivative by integration by parts again. So here's the work over here. Let u equal x to the k plus 1. du is k plus 1 times x to the k dx. Same dv. And so using the formula uv, we get this minus the antiderivative of v du. And that's this mess right here. And we can move the minus sign out front, and we can move the k plus 1 out front, because k is a constant. And so here's what we've got. The antiderivative x to the k e to the minus x dx. So we want to take the limit as a approaches infinity of this term right here, plus k plus 1 antiderivative. This is really 0 to infinity. x to the k e to the minus x dx. We can, once again, use L'Hopital's rule. I'll show you on the next board that this indeed evaluates to 0. You got to apply L'Hopital's rule many times. This is like 0 over 1, which is 0. And over here, here's the key. We're given that this thing evaluates to k factorial from right here. And so k plus 1 times k factorial is k plus 1 factorial, QED. That which was to be proved. And here's board 4, just showing you that this one term where we're taking a limit as a approach infinity does indeed go to 0. Okay, so L'Hopital's rule, we take this derivative up here many times, k plus 1 times x to the k. Take the derivative again, you get k plus 1 times k, x to the k minus 1. Eventually, you get x to the 0. And then you'd have a constant in the numerator and infinity in the denominator. Okay, there you go. Hope that helped. If you have any questions, post a comment.